Today we're going to be talking about the Theorem of Thales, which answers a question for us. That question would be, what can we say is true about a triangle that is inscribed in a circle, or maybe even a semicircle, when one of the sides of that triangle is a diameter of the circle? And we're going to be using Geogebra to just demonstrate this. You can see that here's a semicircle. It would just as well be a circle. That would work as well. And we have a triangle inscribed. And we're trying to say what is true about this triangle ABC. So let's see what happens. Okay, we can see that we're breaking this triangle up into two triangles. And as these sides are growing, notice this is the key, that something is true about these sides, and it is that they are congruent to each other. And when we get them all the way to the edges of the circle, they are congruent to each other. And why would that be? Why are these sides congruent? Because they are radii of the circle. And since these sides are all congruent, what does that say about the angles of these two small triangles? What's true about this blue angle and this blue angle, since this side of the triangle is congruent to this side of the triangle? It means that that angle and that angle are congruent to one another. This is an isosceles triangle. And when you have an isosceles triangle, the two angles formed by the two congruent sides are congruent to one another. Same goes for this triangle, for the same exact reason. An isosceles triangle with two congruent sides, therefore we have these two angles also being congruent. So we have 36 and 54, and so this big angle here is going to be the sum of those two angles that we just talked about, 36 and 54. And what's 36 plus 54? It's 90. We have a right triangle. Now, is that always true? Let's see what happens if we move C around somewhere else. So now that we've moved it to a different spot, we now have the angle of 50 and an angle of 40. Well, these two angles are still the same as those. What's 50 plus 40? 90. What if it goes way over here? You can see, can't see it as well now, but I'll tell you what it says. It says 80, and this is 10. Well, what's 80 plus 10? No need to answer. What if it's all the way over here? What's 79 plus 11? Always 90, no matter where we put it. Even if we put it way over here, this one's getting approaching 0, and this one is approaching 90. Same goes for over there. So this is kind of a proof by seeing. Seeing is believing here. But there are many ways to prove this theorem. In researching it, I saw that there was a way to do it just with basic algebra and geometry. There's a way to do it with trigonometry. There's a way to break this triangle up to extend it into a quadrilateral. That was a pretty cool way to do it. And there's even a way to do it with linear algebra. So if you care to see more about that, feel free to look that up. I found a lot of good information on Wikipedia about the Theorem of Thales. Also, some applications of this is it allows you, if you have a circle, just lay a piece of paper on it, and you'll have one corner of the piece of paper will be on the edge of the circle, and that'll obviously be a right angle. You can see where the piece of paper will intersect the circle, and you can draw a diameter. And then do it again, and you can draw another diameter, put the piece of paper somewhere else. You can draw the diameter a different way. You can see where those two diameters intersect, and you have found the center of the circle. So that's one great application. Another application is that it allows you to find the tangent to a circle. It allows you to construct the tangent to a circle at a given point. Again, if you care to learn more about that, feel free to look that up. Google it, go to Wikipedia, Theorem of Thales, and you'll see those things. Here's just the basic analytical geometry proof just using some basic geometry and algebra. So let's let x equal angle OAC. So x equals this angle. So we're just going to generalize this angle. It's not a constant value. It's any general value we're going to call x. And let y equal OBC. So here's y, angle OBC. So here's y. So if that's the case, then it would follow that angle ACB, this angle up here, is the sum of x and y. If we believe that the two angles formed by the congruent sides of an isosceles triangle are congruent to one another, then that's all we need. That's the key. That's all we need to say this. So then we can say that thus the internal angles of triangle ABC would simply be x, that's this one, y, that's this one, and x plus y, which is the sum of these two, which make up this angle. And since the sum of the angles of a triangle is 180 degrees, then x plus y, that's the three internal angles, has to equal 180 degrees. Then we can combine these like terms, the x with the x, the y with the y, and we get 2x plus 2y equals 180. Okay, what can we do now? We can factor out a 2. If we factor a 2 out, then we have 2 times the quantity x plus y equals 180. Then we can divide both sides by 2, and it leaves us with x plus y must equal 90. And remember, x plus y is angle ACB. So no matter what, angle ACB, whatever these other two angles are, will always be 90. Therefore, we can say that triangle, this should say triangle ABC is a right triangle. And that is the Theorem of Thales.